8.2 is all about classifying figures. We'll specifically be looking at triangles and quadrilaterals in this section. Before we begin, let's take a look at the key formulas that we'll need in this section. To calculate the distance of any side, or the length of any side, we'll be using the distance formula. This works really well, especially when you don't have a graph. However, if you do have a graph, you could also use the Pythagorean theorem by just creating a right triangle where the hypotenuse is the length that you're trying to calculate. Let's go ahead and write that down. Could also use the Pythagorean theorem. And again, remember that this pretty much works when you have a graph. If you don't have a graph, I wouldn't suggest the Pythagorean theorem. The midpoint will be used anytime you're trying to find the midpoint of any side or diagonal. We'll also be calculating the slope when we're trying to classify our quadrilaterals. To do this, we'll be using our slope formula, y2 minus y1 over x2 minus x1. This will allow us to calculate or classify whether the sides are parallel or perpendicular. To calculate your slope, you could also use rise over run, but again, this only works if you have a graph. And I'm also going to put in our notes that these are best for graphs. Okay, so let's go ahead and begin with classifying triangles. For triangles, we're going to classify them as scalene, isosceles, or equilateral. So let's talk about what each of these names mean. A scalene triangle is a triangle with no congruent sides. So let's go ahead and write that down. An isosceles triangle is a triangle with two congruent sides. And last, we have an equilateral triangle, which is a triangle with all three sides congruent. So, if we can calculate the length of each side and just compare them, we'll be able to classify by determining how many pairs of congruent sides we have. So let's take a look at our first example, triangle ABC. We need to find the length of AB, BC, and AC. It would be nice if we could just count horizontally or vertical, but unfortunately all three sides are diagonals, so we won't be able to just simply count the number of blocks. So we have to use one of our other methods for finding the side length. We have our distance formula, which we could use, or we could use the Pythagorean theorem, and this works best with a graph. So I'm going to go ahead and use the Pythagorean theorem in this example, but actually either one will work. So let's find AB. So to find the length of AB, I'm going to go ahead and create a right triangle where AB is the hypotenuse. So what I'll do is I'll create a horizontal and a vertical that makes a perfect right triangle where AB is the hypotenuse. Next, I'll label the sides with what their lengths are. Since this side is vertical, I can count the number of blocks and find that length is 3. The horizontal side is a length of 4. And the diagonal is our unknown. We can label that as anything we want or just keep it as AB. So, what I know is that the side squared plus the side squared will be equal to whatever the hypotenuse is squared, so AB squared. Let's go ahead and calculate this. 3 squared is 9, 4 squared is 16, and AB is still our unknown, so we'll leave it as AB squared. 9 plus 16 gives us 25, so 25 equals AB squared, and take a square root, and we'll get the length of AB. So AB will be the square root of 25 or just 5. Now, earlier in our notes, I told you that whenever we took a square root of a problem, as we did in this step, we need the positive and the negative root. However, my answer was only our positive, and that's because we were finding a side length. It doesn't make sense to say that the side length is negative 5, so that's why I ignored the negative root. Okay, so let's go ahead and move on to BC. So for BC, once again, I'm going to create a right triangle by drawing a horizontal and a vertical line, which will connect our endpoints here. We have a side length of 3, a vertical height of 4 here, and our unknown BC. So once again, we have 3 squared plus 4 squared equals BC squared. Calculate. In this case, it should look pretty familiar because these numbers happen to be the same. You could probably already predict what's going to happen here. Take a square root, and the square root of 25 will be 5. So we just found that BC will be 5 as well. So what we have here are 2 congruent sides. So is it enough to just say, yes, this triangle is isosceles, we're done? And the answer is no. You have to check all 3 sides, because who knows, AC could be congruent or not. If it's congruent and we have 3 pairs of congruent sides, it will actually be an equilateral triangle. So be careful, don't just jump to conclusions. So let's take a look at AC. Once again, we'll create a right triangle. This right triangle has a height of 1 and a length of, looks like 7 blocks across. So for AC, we have 1 squared plus 7 squared equals our hypotenuse AC squared. 1 squared is 1, 7 squared is 49. 1 and 49 make 50. And take a square root of 50. And the square root of 50 is not a whole number, but we could simplify it if we want to break it down into its perfect square factor, 25 and 2. And then 25 actually pulls out as a 5, and since the 2 is not a perfect square, it will stay in as a radical 2. So AC's length is 5 radical 2. So it's definitely not the same as your first 2 sides. So since we only have 2 pairs, or 1 pair, of congruent sides, or 2 matching sides, I'm going to call this an isosceles triangle. And that's our classification. Okay, let's move on to our next problem. In problem 2, we want to do the same thing. Classify this triangle. Here we have coordinates though. So if I have coordinates and I don't have an actual graph, I'm going to use the distance formula to find their lengths. You could actually go ahead and produce a graph and then sketch in a triangle if you want it, and then use the Pythagorean theorem as well. It's completely up to you. But I'm going to go ahead and use the distance formula without a graph. So let's calculate DE. Now, recall that the distance formula will actually be the difference of x's, x2 minus x1 squared, plus the difference of y squared. A lot of students get overwhelmed with this formula, but if you just think of it as literally the difference of x's squared and the difference of y's squared, it becomes much easier to memorize. So let's calculate DE. Our 2 coordinates are 0, 0, and 1, 4. Yes, you could label this as your x1, y1, x2, y2. But as I said, for the distance formula, all it is the difference of x's, so the difference of 0 and 1 would just be 1, right? Plus the difference of y's, so 4 minus 0 squared. Continuing to calculate, we have 1 plus 4 minus 0 gives us 4, squared gives us 16. And our final answer for DE is the square root of 17. Let's go ahead and find EF. For EF, we again have our distance formula. Difference of x's, so our x's are 1 and 5, so the difference would be 5 minus 1 squared, plus difference of y's, so for EF, my y's are 4 and 2, so we're going to go ahead and do 2 minus 4, or you could do 4 minus 2 technically, because when you square it, it actually doesn't matter. It will make it positive regardless of which direction or which point you put first. So 5 minus 1 gives us 4. 4 squared is 16 underneath that square root. 2 minus 4 is negative 2. Negative 2 squared is going to give me positive 4, giving us the square root of 20. 20 is not a perfect square. However, it does have a perfect square factor. 4, which is a perfect square, goes into 20. So we can break this down into 4 times 5, or 2 radical 5. So once again, we look at our sides and we say, oh, those don't match. But we can't just jump to the conclusion that it's scalene just yet. Because if we find one pair of matching sides, it's going to be isosceles. So let's move on to our last side, DF. So for DF, we're looking at the points D, 0, 0, and F, 5, 2. Doing the distance formula, we have difference of x's. Our two x's are 0 and 5, so just subtract them. 5 minus 0. Subtract your y's, 0 and 2, 2 minus 0, and simplify. 5 minus 0 is 5 squared, it's 25. 2 minus 0, 2 squared gives you 4, all underneath the square root. Add those together and you get 29. 29 is not a perfect square. It does not have a perfect square factor, so this is our third side. Comparing our three sides, we notice that none of them match. So since none of them match, this means that this triangle will be scalene. Now that we've classified our triangles, we're going to move on to our quadrilaterals. We're going to classify our quadrilaterals as one of 6 quadrilaterals which we've talked about a lot this year. Before I begin, I want to talk about the properties of quadrilaterals. You should have a piece of paper that looks something like this. It gives a summary of all of the properties of quadrilaterals. Now obviously, to classify a quadrilateral, we can look for all of these properties for each and every one of these quadrilaterals. However, you can tell that would take a lot of time and a lot of work. So, we actually don't need to look for all of the properties of the quadrilaterals. It turns out if we only look for specific characteristics, we can determine if those quadrilaterals are there. If you turn to the back of this page, it'll show how to prove a particular quadrilateral. So for example, for a parallelogram, all we need to do is identify 2 pairs of parallel sides. A rectangle would be 2 pairs of parallel sides and also perpendicular lines, and so forth and so on. So we look for all of these figures. At the bottom of the sheet, I've given a flow chart which tells how these particular items are related. For a parallelogram, we could have a rectangle, rhombus, and if it's a rectangle and a rhombus, then it will be a square. A trapezoid could specifically be an isosceles trapezoid, and a kite is in its own category. I've also summarized these ways in a nice, easy flowchart, which students found very helpful last year. We're going to refer to this flowchart when classifying our figures. We'll obviously start in the Start Here bubble. Each bubble or box will tell you exactly what you're going to do. In the end, you'll move to a particular classification. So we'll begin with classifying all 4 slopes. From here, if it has 0, 1, or 2 pairs of parallel sides, that will tell us which direction to move in and what eventually we'll do next. Let's go back to our examples and begin working. Let's take a look at problem 3. Classify figure ABCD using our most precise name, show all work. Okay, so to classify this figure, I'm going to go ahead and look at my flowchart. Once again, the flowchart tells us where to begin. It says to calculate all four slopes. So let's do that. I know this is going to be tedious, but it will get the job done, and I need to see all of the work before I can give you full credit for these problems. Because yes, you could just easily guess by looking at the figure what you think this figure is. But sometimes when you guess wrong, and it's a lot of points off. So, let's take a look at this figure. Let's classify each side by finding the slopes of each side, beginning with AB. You could use your slope formula, y2 minus y1, all over x2 minus x1. Or you could use rise over run. Rise over run only works if you have a graph, which in this case we do. So I'm going to go ahead and use the graph. It looks like for AB, we rise 4 and run 2. So that will be our slope, 4 over 2. This reduces to 2. Let's find our next slope, BC. BC looks like it rises 1 and runs 4. So our slope will be 1 over 4. Let's find CD. For CD, it looks like we rise 4 and run 2. So we have 4 over 2 or 2. Slope AD will rise 1 and run 4. So 1/4. So it looks like we have one matching set of 2's and one matching pair of 1/4. So let's look at the flow chart and see what we have. So we either have 0 pairs of parallel sides, 2 pairs of parallel sides, or 1 pair of parallel sides. And if you recall, parallel sides are when we have matching slopes. Here we have 2 pairs of matching slopes. So that means we have 2 pairs of parallel sides. The flowchart then tells us to look for opposite reciprocal slopes. Opposite reciprocal slopes are our flipped and opposite signs. 2 and 1/4 are not flipped nor opposite. So our answer would be no, and we would go left in our flowchart. We would move on to the next box, which tells us to calculate the length of 2 adjacent sides. Adjacent, if you recall, means near. So they should be sides connected to each other. So pick any 2 sides. So let's suppose I start with AB. If I want to find the length of AB, I'll use either the distance formula or the Pythagorean theorem. Once again, since I have a graph, I'm going to go ahead and use the Pythagorean theorem. I'm going to erase my dotted lines that I use for my slopes, just to clean it up a little bit. And I'm going to sketch in my right triangle. Here I have a right triangle with a height of 4 and a length of 2, and our diagonal is the hypotenuse. So for AB, I have 4 squared plus 2 squared equals the AB length squared. Simplifying, I have 16 plus 4 equals AB squared. And once again, simplifying, I get 20 equals AB squared. To calculate my AB and get rid of my square, I'll take the square root, leaving me with the square root of 20. If you would like to reduce this radical, it would reduce to 4 times 5 underneath the square root, and then once again to 2 radical 5. So 2 radical 5 is the length for AB. Next, I want to find the length of any side adjacent to AB. So I could pick BC or AD. You don't want to pick CD because it is clearly not attached or next to AB. So let's suppose that I pick BC. I'm going to go ahead and swap to a different color here and do pink. And I'm going to sketch in a right triangle for BC. Here I have a side of 1 and another side of 4. So for BC, I will have 1 squared plus 4 squared equals BC squared. So I get 1 plus 16, which will equal 17. And taking the square root, I see that BC is equal to the square root of 17, which is a prime number, so it doesn't have any factors at all, other than 1 in itself. So taking a look at those two lengths, I go back to my flowchart. And I see I want to check to see if the two lengths are the same. So are they equal or not equal? And in this case, they're not equal. And the flowchart tells me that this is a parallelogram. So that's my answer. If you originally looked at this and thought that it was a rhombus, notice that you would be wrong. So that's why it's very important that you don't just assume that you can guess the name of this figure, because looks are deceiving. That's why all of the work is very, very important and necessary. Okay, let's move on to the next problem. Problem 4. Figure MNPQ has vertices M01, N, -14, P, 25, and Q, 32. What is the most precise classification of MNPQ? Once again, I'm just going to follow the flowchart. If I look at my flowchart, I see I need to first calculate the slopes of all four sides. So let's go ahead and do this. Since I don't have a graph, I'm going to go ahead and use the slope formula. The slope for MN. Now, here, order does matter, so you may want to go ahead and label your points. I would do this in pencil because you may need to erase and relabel your points. So let's go ahead and calculate. Our slope formula is y2 minus y1, so in this case, 4 minus 1. And on the bottom, we have x2 minus x1, so -1 minus 0. Simplify your top and bottom. So we get 3 over -1. Once again, simplify your fraction if possible. And in this case, 3 divided by -1 is just -3. I'm going to keep going here. Slope of NP. Now, I'm going to relabel because I have a new set of points. So I have x1, y1, and x2, y2. Difference of y's on top, so 5 minus 4. Difference of x's on the bottom, 2 minus a -1, gives us 1 over 3, so 1/3. Our next side is PQ. Once again, you could relabel your points if needed. So PQ would be x1, y1 for P, and x2, y2 for Q. Difference of y's, so y2 minus the y1 over difference of x's, 3 minus 2. Gives us -3 over 1, and we simplify if possible, so -3. One last slope to calculate, and that would be MQ or QM. Last time, relabel your points. x1, y1, and x2, y2. By the way, it doesn't matter which point out of the 2 points is your x1, y1 or x2, y2. It just matters that you're consistent. And that's why it's important to label and keep them consistent with your slopes. y2 minus y1 gives us 2 minus 0. The denominator is our difference of x's, x2, 3, minus x1, 0. Simplifying gives us 1/3. So it looks like we have 2 pairs of matching slopes or 2 pairs of parallel sides. Let's check out our flowchart. 2 pairs of parallel sides will once again take us straight down. Next, they're going to ask us, are the slopes opposite reciprocals? So in other words, are the slopes flipped but opposite signs? Well, if you flip 3 or 1/3, you'll get each other. So 1/3 flip gives me 3, and 3 flip gives me 1/3. And one is positive and one is negative, so they are opposite signs as well. So I would answer this question with a yes. Taking me to the right. Next, I want to calculate the length of 2 adjacent sides. so two sides next to each other. Because I don't have a graph, I'm going to resort to the distance formula in this problem. So let's go ahead and just pick mn. To find the distance of mn, I'm going to need to label them x1, y1, and x2, y2 once again. Or you can recall, it's just difference of x's squared plus difference of y squared, all underneath a square root. So for mn, difference of x's would be -1 minus 0 squared, or you could have done 0 minus -1 squared, which would have also worked, plus difference of y squared, so 4 minus 1 squared. Calculating, -1 minus 0 is -1. Square it, we get 1. 4 minus 1 is 3. Squared, we get 9. Giving us square root of 10. 10 does not have a perfect square factor, so that's as reduced as it gets. We'll calculate an adjacent side, a side next to mn. So if you can't think about what mn/pq looks like, you may want to even draw it out. mn/pq, if it helps. So we calculated mn, so to calculate an adjacent side, we would need to do np since it's attached, or mq. I'm going to go ahead and do np. Since I'm dealing with a new set, I'll relabel my points. Okay, so difference of x's, in this case, 2 minus -1 squared, plus difference of y's, looks like we have 5 minus 4 squared. And simplify. 2 minus -1 is positive 3. Square that, you get 9. 5 minus 4 is 1. Squared, 1. And simplifying, we get 10 underneath the radical, giving us square root of 10. So it looks like our adjacent sides do match. Let's see what the flow chart says. Calculate the length of adjacent sides. Are they equal? Yes, they are. Let's scroll down, and that will tell me I have a square on my hands. And that's the name of the most precise name. Okay, and I believe we have one last problem. 5. A kite is shown below. What is the most precise classification of the quadrilateral formed by connecting the midpoints of the sides? So this problem is more complicated. They're not asking us to classify the figure here. They're asking us to classify a figure that we have to first create. So the first thing we have to do is find the midpoints of every side. In a graph, this isn't so bad. You can essentially just figure out where the middle of the two points are. So for example, for ki, we have a horizontal distance of 4 and a vertical distance of 4. That means that the midpoint will be horizontally 2 over 2 and up 2. So this is our midpoint of ki. For it, it looks like we have a vertical height of 4 and a horizontal distance of 8. So that means that our midpoint will be vertical 2 and horizontally 4. We can use the same idea to find our other two midpoints. I'm going to go ahead and label those new points with new names. So I'm going to call them A, B, C, D. So that way when I'm finding their slopes and side lengths, you know what segments I'm referring to. This is the figure that I want to classify. Once again, before you just look at the figure and say, oh, it looks like such and such of a figure, you want to go ahead and prove it with your slopes and your distances. Otherwise, you won't get full credit. So we turn to the flowchart. The flowchart tells us to calculate the slope of each side. Since I have a graph, I'm going to use the rise over run. So for AB, it looks like it rises 0 and runs 6. So our slope is 0 over 6 or 0. For BC, we rise -4 and over 0. So -4 over 0 is actually undefined. CD's slope will be up 0 over 6. Slope of 0. And AD looks like it goes up 4 over 0, or undefined. So we have two matching pairs of parallel sides. Two matching pairs of parallel sides will take us down yet again. Next, we'll check to see if the slopes are opposite reciprocals. 0 undefined. It's kind of confusing what undefined really means. Undefined is when you're dividing by 0. Undefined can also be written as 1 over 0. So if you look at these, this is actually a special case of opposite reciprocals because it's flipped, and technically, since 0 doesn't have a sign, they are also opposite signs. So if you ever see 0 and undefined, those are indeed perpendicular lines. So, yes, we do have opposite reciprocals. Next thing we'll calculate is the length of two adjacent sides. One side is AB. Since it's a horizontal line, I can just count the number of blocks and find that the length is 6. An adjacent side would either be BC or AD. If I calculate BC, it's vertical, so I can count the blocks and just get 4. Looking at these two sides, I notice that they are not equal. So according to my flowchart, when they're not equal, this tells me this figure is a rectangle. And that's the name of this figure.